This is lesson 1-9, arithmetic sequences. In this lesson, we're going to describe the relationships and extend terms in arithmetic sequences. In the mini-lab, it says use centimeter cubes to make the three figures shown. How many centimeter cubes are used to make each figure? In figure number 1, you can see there are 4. Shows us that down here in the table. Figure number 2, we add another row or another layer. So in figure 2, there's 8. Figure 3, a third layer of 4. So in figure 3, there are 12. So what pattern do you see? Well, I think that if you look at this, you can see that for each figure, you're adding 4 cubes to the figure listed. So figure 4 would be 16, figure 5 would be 20, figure 6 would be 24, figure 7 would be 28, figure 8 would be 32. Question number 4, how many cubes do you need to make the 10th figure? Well, let's add 2 more here. 9 gives us 36, and 10 would give us 40. So the answer to the question number 4 is we need 40 cubes to create or complete the 10th figure. A sequence is an ordered list of numbers. Each number in a sequence is called a term. In an arithmetic sequence, each term is found by adding the same number to the previous term. An example of an arithmetic sequence is shown. You can see here 8, 11, 14, 17, 20 is our sequence. The dot, dot, dot means it continues on. And you can see that they're adding 3 to each previous term to get the next term. Example 1, it says, describe the relationship between the terms in the arithmetic sequence 8, 13, 18, 23. Then write the next 3 terms. And again, here you can see that they're adding. In this case, they're adding 5 to each term, previous term. So 8, 13, 18, 23. To find the next 3 terms, we would add 5 to 23 gives us 28. 5 to 28 gives us 33. 5 to 33 gives us 38. Check your progress. Now let's try that. When we examine this, we can see that our values are increasing, so again that means we're adding. It appears here that we're adding 13 to each previous term. We test that out. We see that it's correct, so our next 3 terms would be 39 plus 13, which is 52. 52 plus 13, which is 65. 65 plus 13, which is 78. In our second example, it appears that we're adding 3 to each previous term, and we test that and we see that that's true. So our next 3 terms would be 13 plus 3, which is 16, 16 plus 3, which is 19, 19 plus 3, which is 22. Arithmetic sequences can also involve decimals. In our first example here, we have 4 tenths, 6 tenths, 8 tenths, 1. So we're adding 2 tenths to each previous term, as you can see here. So we continue that. So 1 plus 2 tenths would be 1.2. 1.2 plus 2 tenths is 1.4. 1.4 plus 2 tenths is 1.6. In example C, it appears that we're adding 3 tenths to each previous term. We test that. We see that it's true. So our next 3 terms would be 1.9 plus 3 tenths, which is 2.2, then 2.5, and finally 2.8. In example D, it appears that we're adding 5 tenths to each previous term. We test that. We see that it's true. So we add 5 tenths to the next 3 terms. 4 plus 5 tenths becomes 4 and 5 tenths. 4 and 5 tenths plus 5 tenths becomes 5 and 0 tenths. And our final term, 5 plus 5/10 becomes 5 5/10. In a sequence, each term has a specific position within the sequence. Consider the sequence 2, 4, 6, 8. This is the first position, this is the second position, the third, the fourth, the fifth, and so on. The table below shows the position of each term in the sequence. Notice that as the position increased by 1, the value of the term increased by 2. So we actually have two patterns here. One for the position and one for the value of the term. You can also write an algebraic expression to represent the relationship between the term in a sequence and its position in the sequence. So what we're doing is we're going this way. We're going horizontally now. In this case, if n represents the position in the sequence, we can simply take that position and multiply it by 2. This would be the expression, the algebraic expression that would describe this pattern. You can see here that 2 is the coefficient of n, which we know means 2 times n. The homemade greeting cards that Meredith makes are sold in boxes at a local gift shop. Each week the store sells 5 more boxes. So week 1 we have 5. We can see that down here in our table. We can see it in our diagram here. Week 2 we have 10. Week 3 we have 15. So the algebraic expression that describes this, as we look horizontally here, the position times 5 gives us the value of the term. So our algebraic expression would be n times 5. Notice how we rewrite that with the coefficient of 5. We eliminate the raised dot. So the expression, the algebraic expression that describes this pattern is 5n. So when they ask us what the value of the 100th term is, we simply replace the variable with 100. We multiply and we see that the value of the 100th term is 500, which saves us completing this table, which would be very time consuming if we had to go all the way out to 100. If the pattern continues, what algebraic expression can be used to find the number of circles used in the 50th term? How many circles will be in the 50th term? Well, figure 1, we have 3. Figure 2, we have 6. Figure 3, we have 9. So we can see that these increase by 1, that these are increasing by 3. If we go horizontally, if we use n for the number of the term, we can see here that we're multiplying that times 3. So the algebraic expression that describes this pattern is 3n. So to find the 50th term, we simply take 3n, replace the n with the 50, and so our 50th term would have a value of 150. Let's work through a couple examples here. Describe the relationship between terms in each arithmetic sequence, then write the next 3 terms in each sequence. So number 1 is 0, 9, 18, 27. It appears that we're increasing by 9 here. So our next 3 terms would be 36, 45, and 54. In example 2, 4, 9, 14, 19, it appears that we're increasing here by 5. So 24, 29, 34. In example 3, problem 3, we have 1, we have 1 and 1/10, we have 1 and 2/10. So it appears here we're increasing by 1/10. So our next 3 terms would be 1.4, 1 and 4/10, 1.5, 1 and 5/10, 1.6, 1 and 6/10. And in our last example, 5, 5.4, 5.8, 6.2. It appears that we're increasing by 4/10. So our next 3 terms would be 6.6, 7.0, and 7.4. The table shows the height of a certain plant each month after being planted. If this pattern continues, what algebraic expression can be used to find the height of the plant at the end of 12 months? Find the plant's height after 12 months. So we want to skip from 4 down to 12. We can see that we're increasing here by 1. We can see that we're increasing here by 3. If we go horizontally and we use n as the value for the month, we can see that we're taking that value times 3. So our algebraic expression that describes this pattern would be 3n. So we take 3n. We replace it with the n with a 12, and after the 12 months, the height of the plant will be 36 inches. Here's your answers to all those questions. If you want to go back and check them, rework them. Here's your vocabulary for this lesson: sequence, term, and arithmetic sequence. You're expected to know these, so memorize them. You'll be evaluated at some point during the chapter. You'll be expected to know them. At this point, you should quit the video. Go back to the Scott Highlands homepage. Go to the Moodle login link. When this page shows up, the login page, your username is your 6-digit student number. Your password is the first 6 digits of your last name and your 2-digit birthday.